Okay, I think we'll get started. So today, an important day, we're going to talk about Coulomb's law, and this will tell us how to calculate the force between two charged objects. So let's imagine we have two charged objects. We charge Q1 and Q2, separated by a distance r. Okay, so this is our most basic thing we can have here, where we have interacting objects via electrostatic forces. Now, if we were to draw a free body diagram for Q1, right, there will be a force acting on it. Let's say these are both positive. Then there'll be a pushing force, and the action-reaction pair will be on this. The free body diagram for this, we'll get a push here. This would be the force of 1 on 2, and this is the force of 2 on 1. Okay. Now, I'm writing this a little bit sloppy here. Force is a vector. I'm not writing these as vectors here, just as magnitudes, and then we'll have to think about the direction at which they're pointing. So the magnitude of 1 on 2 and 2 on 1 are the same, and we'll call that F12. And so F12 is determined by the size of the charges, Q1 times Q2, divided by the distance squared. And so Coulomb's law is really a law stating that the strength of the electric force drops off as r squared. And then there's this constant, which is called Coulomb's constant. Which is 8.99 times 10 to the 9 newtons meter squared per Coulomb squared. Now, sometimes often you'll see me write, instead of K, 1 over 4 pi epsilon naught. I'm just maybe more used to that. Epsilon naught is a more fundamental constant of nature, if you could claim that, than the Coulomb's constant. This is the permittivity of free space, and units here, seconds, Coulomb squared, kilogram per meter cubed. And so we certainly could write something like that. Now, let's get back to this vector idea. So this is the magnitude. The force vector, as the free body diagrams are indicating, is along this axis between these two. And either it's a repulsive force pushing these away. So if we look at this, it's experiencing a force in this direction, this experiencing a force in this direction. Or if it's an attractive force, then the free body diagrams would look like that. This would experience a force in this direction with this as the agent. And then this would experience a force in this direction with this as the agent. So we have to think about the vector sum, or the vector, not the vector sum yet, the vector associated with these magnitudes, right? And again, it's directed along the line between the charges. Now, we have a very important concept here, and that is this idea of superposition. And the force, the electrostatic force, is superimpose. So the electrostatic force for object J is the sum of the individual pairwise Coulomb forces from all the surrounding charges. And so F total, and this is added vectorially. Okay. So F total is this is going to be the vector sum of 1 with J, 2 with J, up to n with J. Okay. And so, for example, if this was the free body diagram, and let's say these were all positively charged, then we would have say F1J in this direction, F2J in this direction. This one would be FNJ, and so on. And so the net result would be the vector sum of all the individual pairwise forces. All right, let's just do a quick example here. Let's put three charges on a line. We'll go positive, negative, positive. 3 Coulomb, 3 times 10 to the minus 7 Coulomb. This is a negative charge of 1 times 10 to the minus 7 Coulomb. So very often we would write that as negative. And then again, positive 3 times 10 to the minus 7 coulombs. So the total, let's call this 1, 2, 3. Let's look at the total force on 3. So the total force is going to be Coulomb's law for 1 on 3, right? That's going to be this. So that's going to be 3 times 10 to the 7th times 3 times 10 to the 7th, right? Coulomb's law, over this distance, which is 0.25 centimeters, 0.25 centimeters squared, and then multiplied by Coulomb's constant. Well, that's just one term, and that's in this direction, right? That's in this direction. Now, let's look at this on this one. Well, we can think about it a couple of ways. We can use the negative charge, and that will take care of the attraction. So we could go plus K negative charge, and then the charge of 3. And so again, Coulomb's law here, containing the minus sign within the charge. Alternatively, we could think of this as the absolute value of the charge and then indicate this as an attraction. So this would be pulling this way and use the negative sign. So we can think about this a couple of different ways. So it's always good to not just follow the numbers, but really make sure we know what's happening. Well, and actually, I should have done this in the first place, is draw a free body diagram for this. We're going to get a 1-3 force in this direction, and then we're going to get a 2-3 force in this direction. And the net force will be whatever we calculate these to be. All right, so these are going to counteract each other, and this minus sign is taking care of that for us. We see that overall, we just barely get a little bit net negative. So although this charge was less, this is closer, and then being squared, that amplifies that closeness. And so we end up, I think this works itself out to be 0.001 newtons of force. All right, well, this is on a line. Let's make this a little more complicated. Let's go back to that trigonoplanar design that we saw when we have 3 charges and they want to get as far apart as possible. They'll form, if they were locked in this cylindrical or this disk, they would form a trigonoplanar, and we would have equal distance. And just to put some numbers in so that you can check this, let's call these 0.1 meters. Oh, do I want those as meters? Yeah. 0.1 meters. 10 to the minus 6 coulombs. Now, let's put this on a coordinate system, and I'm going to turn it just a little, and we're going to look at the force acting at any one of these, right? There's some symmetry here, so any one of these. If I angle it this way, then I can split my 60, it's an equilateral triangle, 60, 60, 60. I can split that 60 as a 30, 30. And then I can write my y component, right? So these are all negatives. So here we're going to get a force in this direction from this one, and the free body diagram in that direction for this one. Now, let's calculate this. So we know now that we're going to calculate a magnitude, and it's going to be the vector sum of these two. And so at the end of the day, we're going to be pointing this way. So let's check our y components. Well, that's going to be sine of 30 times Coulomb's law. Well, we're equal charge, so that's just going to be q squared, Coulomb constant, and then the distance squared. Now, we have sine of minus 30, and the same Coulomb's piece of Coulomb's law here. Sine 30 and minus sine 30 are equal magnitude, but opposite sign. So these two components are going to sum to 0 and give us 0 net force in the y direction, which is precisely what we expect from our picture here. So that's good. Next, we calculate the x component. Well, that's going to be cosine 30, and then cosine minus 30, but the symmetry of cosine is such that those two are equal. So cosine minus 30 equals cosine 30. So this is just going to be 2 times cosine 30 times the Coulomb's law component. And I think this works out. You can check this, and I think this works out to 150 newtons. These are probably centimeters, actually. 156 newtons. Now, what direction is this? That's in this direction. Okay, so we should write to the left. We could also put a negative sign there to indicate to the left as well. Okay, so this is Coulomb's law. And again, get this down. You want to essentially memorize that. I think that would be nice. Of course, you can always look it up, but good to get it really internalized so that it's just boom, right there for you. Charge times charge divided by r squared. And you'll probably forget the actual values here, but you can always look those up. But you want this functional form. The force drops off as r squared. And so we're going to see that when we talk about ions and ions interacting with each other. So we'll see that throughout or coming up various places in the course. Anytime charges interact, we're going to see that. And next time what we're going to do, before we go to full hydrogen, which is going to involve some additional concepts, we're just going to treat hydrogen as or treat atoms, I guess, in general, as a Coulomb's law situation. And so we'll take an intermediate step from here, what we've been talking about with charges, to atoms, until finally we get to the actual way atoms behave, at least at the level of our introduction to physical chemistry course. So practice the homework problems. Any physics book that you have will have lots of problems on Coulomb's law. You should be able to find plenty of problems, and just make sure you get yourself really good at that.